To this point, we've determined the electric field lines just from symmetric charge distributions, the spherical symmetry from the point charge and the cylindrical symmetry from the infinite line of charge. We will now consider the field produced by a charge distribution that does not possess a global symmetry, namely an electric dipole, two equal magnitude but oppositely signed charges as shown. We know how to calculate the field from these charges. At any point, just calculate the field produced separately by the positive and negative charges and then take the vector sum. One way to represent this dipole field is to draw a small arrow at every point in space in the direction of the field and then indicate the magnitude of the field by the color of the arrow as shown. This picture reinforces the idea that the field exists everywhere and intuitively displays the main features of the field, its direction at any point, and where it is big and where it is small. How do we represent this field using electric field lines, though? We know field lines originate on positive charges and terminate on negative charges. The direction of the field at any point is given by the direction of the field line that passes through the point, and the magnitude of the field is proportional to the density of the field lines that pass through a surface perpendicular to the field direction at that point. When we follow this procedure, we obtain the curved field lines as shown. We'll now examine some features of the dipole field as inferred from these field lines. First note that the direction of the field at A and B, pointing in the plus x direction, and at C and D, pointing in the minus x direction, agrees with what we've determined in the previous lecture. From the density of these lines, we see that the field is strongest in the region in between the charges. This makes sense since the fields from the positive and negative charges generally point in the same direction there, as opposed to opposite directions in the regions on either side of the charges. We also see that the strength of the field decreases as we move away from the charges, as expected from Coulomb's law. We'll now use this dipole field to further illustrate the main features of Gauss's law.